Okay, great. So I want to welcome Assistant Professor Paul Plucinsky from USC, the Department of Aerospace and Mechanical Engineering. Is that right?
That's right.
Yeah. Paul is a theoretical mechanician, but most importantly, he's a Wolverine.
Go blue.
He got his bachelor's from the civil department here, followed by a master's from the structural mechanics program. And then he went on to do his PhD at Caltech in mechanical engineering. And then he did a postdoc in aerospace engineering and mechanics at University of Minnesota. And that's where I met Paul. Our postdocs overlapped. In fact, we had the same advisor, Dick James. And since then, he's been at USC since 2020.
Since the start of the pandemic.
Yep,
yeah.
good time.
Great timings. Right?
Yep. So today he's going to talk about origami and kirigami. So very cool stuff. Lots of cool pictures coming our way, right?
Lots of cool pictures
right.
and some equations, but so hopefully that's okay. Yeah, so thanks, Ashley, for the introduction. And it's my pleasure to be back at U of M. It's actually have some of my family in the audience, which is kind of cool. We're local, so I got to visit my family while coming and giving a seminar, which is kind of cool. I'm going to talk to you guys today about how you would think about maybe modeling origami and kirigami structures, taking a kind of a mechanics point of view, and really thinking about problems on both the design of these systems in a very systematic way, as well as you see some of these types of systems. And I have a toy that was made by a high school student who is more talented at origami than I am. But this is a nice classical pattern. It's like the pattern that I'm showing you here in this picture. And you can do a bunch of simulations on it, and you can predict sort of its easy modes of deformation where it just kind of wants to collapse on itself. But a lot of interesting mechanics emerge when you just start loading it. And so if you load this thing, what happens is you see like this very robust saddle-like shape. So it curves in one direction this way, and it curves in the opposite sense this way. If you take a conventional sheet of paper, you try to bend it, you just bend it in one direction. So something about the fact that this is a corrugated pattern is leading to this very interesting kind of mechanics. And I say it deforms like a saddle, but really what's actually deforming like a saddle is some average shape, because this thing is oscillating a lot. And so its average is deforming like a saddle. And some of the questions we're interested in are, how do you replace all these little unit cells with something that's homogenized and averaged in the right way to get the response that you expect, which is this saddle, or to start predicting responses. And so I'm going to talk a little bit about design and modeling in that context. First, I want to acknowledge this is work that's done by a lot of people, including myself. My work on origami started when I was a postdoc working in the same group as Ashley with Dick James. We worked with Ben Fang, was a PhD student with Dick James. He's a very good student, and we ended up having this very international collaboration where I was in Los Angeles, Fan was at Cambridge, Dick was in Minnesota, and we collaborated with people at Peking University. And so we could never find a time to meet together because there's just no time that makes any sense for all of us. And then, and then I started working on kirigami, which is more work in progress. And it's with a couple of young professors, Ian Tabasco and Paolo Celli at Stony Brook and UIC, and my postdoc, Yu Zhang, who just recently got a faculty job at Drexel University. And so, so a lot of credit goes to these people. And I'm going to study origami and kirigami, or sort of more broadly, mechanical metamaterials. And so what is a mechanical metamaterial? So very loosely speaking, you have some sort of pattern system, often periodic. So you have a lot of these kind of repeating cells. And if you look at the constituents of the pattern system, what you see is you have very stiff elements, which I would call the panels in an origami structure, and flexible elements, which are the creases. In this kind of planar kirigami system, the stiff elements are like panels, and then the flexible elements are actually these little tiny hinges that you see here. They're flexible elastic elements. you can have these kind of 3D structures at very different scales. So this is 20 microns, and then this is like tabletop. Again, you have stiff elements like bars and flexible elements like the nodes, or this is kind of 3D origami. So it's you have panels and you have creases and you have holes and you have everything. You know, we're pretty good at manufacturing now, so you can make all these things. You can make all these things out of various different types of materials and at almost any scale, the small scales or the large scales in 2D, and you can create surfaces. And essentially, it's a very promising template for doing a lot of you know, tunable design and developing interesting engineering scale properties out of these tiny little complex unit cells. But you know, it's a very large design space, right? So you know, how do you design the unit cell to get a desired property? How do you actually navigate the design space? So questions that I'm really interested in understanding are, is there a way to do a little bit of mechanics? You can start to navigate the design space in some systematic way. And you know, once you maybe think you understand the design space, and you just take one of these things and you start playing around with it, oh, they deform in all sorts of interesting ways. Can you find ways of modeling this that are not so computationally expensive and do a little bit of modeling informed design, sort of kind of go back and forth and iterate in this type of process? And so that's the types of questions I'm interested in. Here's a, you know, I say the design of a mechanical metamaterial is challenging, and I do it by this series of examples. Here's a bunch of examples of mechanical metamaterials and all the interesting properties they may have. This is a 3D auxetic. You can get tunable compression, self-folding at the micro scale, the macro scale, and this novel bending property that I sort of showcased with this toy model. But there's something interesting about this, all these research papers and this sort of system is, anybody have any ideas? What's kind of interesting about this? Well, they're all the same material, or they're all the same design. So, you know, if, you know, and this is not strictly true, but, you know, the design space of a mechanical metamaterial is large and highly tunable. But what we often see when we're trying to actually do something with applications is people often use just the most well-known designs. And why they do that is because, well, typically there aren't a lot of opportunities for easily adapting a design to fit a specified task. And so one broad research goal of mine is to really, how do you make tuning a reality in these types of systems, where if I want, you know, the Poisson's ratio to change by like 0.5%, I should be able to modulate my design in a way to do that. But it's not always very easy to do that in these types of systems. So we're interested in understanding that. A second challenge is really a modeling challenge. So, you know, if I have this mechanical metamaterial here, what's the sort of conventional way you might approach this problem? Well, you can put your sort of structural engineering cap on, and you go, okay, there's too much going on with, you know, this 3D solid here, or this 2D solid here. So let's replace it with bars and hinges. And so you can do something like this, and you have a bar and you have hinges, and you typically have, you know, the bar stiffness, which is much larger than the hinge stiffness. And you can run numerical simulations on these types of systems, and you can do sort of linear perturbation analysis to understand the kinematics. And you do that and you look for small eigenvalues and explore the kinematic space of this design. And you do it perturbatively. You can learn some things about the design space and the kinematic space. But of course, you know, in this particular example, if I want to change the design a little bit, well, then I have to start over and, you know, get these bars and hinges and then tune the hinge stiffness and essentially work on this new design and try to understand its kinematics. Maybe we're not getting the whole kinematic landscape. And while this is a very reasonable thing to do, in terms of trying to, at the early stages of a design and modeling task, you want something that's a little bit more efficient than sort of doing these types of bar hinge methods. So is there a way to actually average the system and try to understand kind of an effective behavior? So what's common among all these systems is that they're made of these unit cells. there are many of these unit cells, you might expect that when you try to understand a limit or an approximate limit of many unit cells, that in some way you can systematically average them and develop continuum, sort of classical continuum constitutive models where you replace the metamaterial itself with just some sort of actual continuum. And then, you know, all the design parameters of the metamaterial are buried inside this constitutive model. Maybe you could start to go back and iterate and do some modeling informed design. So I'm going to give you a flavor of, you know, design and modeling of these systems in this talk. In the first part of the talk, it's going to focus on origami, where we're really trying to expand the design space. We're essentially thinking about things like the mirror aura, which is this example, but what happens if you start playing with the design parameters in a systematic way to develop sort of generic patterns that will approximate fairly generic classes of surfaces. And then I'm going to talk about the modeling problem, which is, you know, I want to replace this complex mechanical metamaterial with some homogenized structure. And I claim that this kind of metamaterial system can be reasonably approximated by an effective field theory, which is described by the equations that I'm showing you on the right, and I'll explain how that actually works. So that's the goals of this talk. Okay, so origami. Why study origami? Well, lots and lots of problems in sort of engineering involve kind of taking some sort of structure and collapsing it down into a very small surface area and deploying it and then turning it into the functional structure that it's supposed to be in. Very common examples are, you know, the James Webb Space Telescope has this very sophisticated unpacking property. So you have to pack up the telescope into a rocket, and then you unpack it, and it's kind of cumbersome, to be honest, this unfolding process for the James Webb Space Telescope. But anyway, they succeeded in this very recently, so it took them a long time, but it's cool. Similar things apply with stents, right? You have to take if you know your arteries are clogged, you got to take this tiny stent, you kind of shrink it down and you put it up, you know, I think it starts here, right? I mean, I don't know, I'm not the expert in this field. And then you bring it all the way to the brain and then you expand it. So, you know, thinking about strategies for how you might design the meshing that deploys the structure is interesting. And so one basic question is, can, you know, origami address these types of problems? It's a recipe for folding and unfolding things. So in principle, it should be able to address problems where you're trying to understand how to package things in tight spaces and then deform them in some systematic way. And, you know, I'm not going to claim that I'm addressing any of these types of applications, but we're learning a lot about how you might generally approximate surfaces using origami. And so to just sort of highlight, we have a tool in place where we can basically take many surfaces and try to approximate them by a certain origami crease pattern. And what this deployable origami pattern does is it starts out as something that's flat and easy to pattern, and then it has a continuous one parameter family of motions which achieve this type of surface. And in fact, then it can actually fold all the way into this fully kind of packaged state too. So that's a property. And so that's what we're trying to understand. And, you know, something that's really important to keep in mind in terms of engineering origami is deployability. The idea that something is easy to fold is not an easy thing to enforce. It's a key requirement in many engineering applications, but you'll see, you know, the very famous origamists, it's actually not a key requirement for folding origami. They actually enjoy it when it's hard to fold. So they've developed lots of interesting recipes to fold origami, like these ones, which are not good for engineering. So here's a few examples of the types of algorithms that people have developed in the origami community. So, you know, Robert Lang can basically make any type of insect using an origami inverse design scheme. And this is an example by Tomohiro Tachi and Eric Demain of a bunny rabbit. And, you know, these are, you know, they're very smart people, but they're also origami enthusiasts. They like the challenge of taking this pattern and folding it into this shape. So they developed algorithms not with practicality in mind that it should be easy to collapse, but with the idea that, oh, I can, if I play around with it long enough, and you can actually see Tomohiro Tachi do this if you go on YouTube. He has a 16-hour video of him trying to fold this. I think that he takes some breaks, but he ends up getting there. But it's not a practical engineering strategy. So, this is the state of the art in origami design, and I'm never going to be able to design surfaces that do this. But you're never going to be able to use your favorite engineering material or actuation strategy to do this either. So I'm not competing with them. So that's good. The folding process here is far too complicated for practical engineering. And so I want to kind of revisit this mirror origami, the simplest origami. So this is what I have here, right? So you take a unit cell. If I had a piece of paper, which I actually don't use anymore now since COVID, and you have the iPad, and you can just write on the iPad. But if I had a piece of paper, what I do is I show you, oh, well, how do you get this design? Well, you can just take a piece of paper, fold it in half again, open it up, and then change the mountain valley assignments, and you'll have this design. And I don't know how Mira actually came up with the design, but it's a very natural thing to do. And you just repeat this pattern. You pattern the mountain valley assignments in the right way. Red is for mountain, blue is for valley. You end up with this kind of crease pattern, and it folds by a very easy motion. So this has this planar motion, which you see here. So you start here, and it will fold, and you can collapse it down. And so it has this very easy planar motion. With very little actuation, you can get it to deploy into that type of shape. And this is really the workhorse and kind of the starting point for engineering origami. And what we were interested in, this was a while back, was, can we sort of generalize on these ideas? So you have a crease pattern. Let's stick with quadrilateral crease pattern, which is basically, it's made out of quads. Every vertex has 4 creases going into it. And flat foldable, so a necessary condition for flat foldable is that you look at this four creases, you look at the sector angle here, and you look at the sector angle here, they sum to pi. These two sector angles sum to pi. So impose those constraints, but then just ask a basic question: what are all the designs? All of them. So let's try to find all the designs. And we call this rigidly and flat foldable quadrilateral mesh origami. Okay, I didn't choose the name. This is the name that Robert Lang is one of the famous origamists. So he says you should call this that, and I'm like, okay, because it's very it encapsulates everything that this is. It's rigidly and flat foldable quadrilateral mesh origami. So let's see if we can develop a design principle for this. So how does this work? So there's nothing fancy here. It's basically, there's a lot of accounting, but I'm going to do mechanics on this problem. So, if you want to understand how to fold all these complicated origami, you have to know how to fold origami at a single vertex. So just to take a single vertex, isolate it. Okay, it has 2 sector angles. It has sector angle alpha, beta. This is pi minus beta. That's pi minus alpha. And you just have to ask, well, what does it mean to fold as origami? So if you think about it for a while, I can sort of sit here and I can pretend that this thing doesn't move, right? Then what has to happen here? Well, this panel has to rotate along this tangent by some angle. That panel has to rotate along the tangent T1 by some angle. And then, this one has to rotate in some more sophisticated way. And you can sort of work out what the sophisticated way is. But these rotations have to be consistent. And at the end of the day, you end up with an equation which says, oh, I folded this thing as origami if and only if I have this product of rotations about these tangents that I'm showing you equal to the identity matrix. So you just turn it, you do a little bit of compatibility and continuum mechanics, and you have a statement, a mathematical statement about what it means to fold origami at a single vertex. Okay, that's nice. So just got to solve that problem. This problem is actually not that bad to solve. So there's a little bit of algebra to do, but you can solve it explicitly. Sort of the most important point to take away is basically this. If I hand you one, if I tell you how you're folding along one crease, so you fold along one crease, and I told you what the mountain valley assignments are. So the mountain valley assignments are like, this is a mountain, this is a mountain, that's a mountain, that's a valley. There are only two choices of mountain valley assignments. So I gave you one of them, and I told you what you were doing along that crease, and you know everything. So everything else is imposed. Yeah.
So I think I understand the rotation, but what about the finite depth of finite?
Yeah, that's a necessary condition. It's a well-known necessary condition. It's called. It's necessary for flat foldability. So it's a necessary condition for folding completely flat. So what people have done is they thought about what it, think about classical paper folding. Like, so you're trying to fold something flat, and then you unfold it and you look at what the angles are. So people realized a long time ago, I think it was Kawasaki realized a long time ago, that opposite sector angles always sum to pi when you're trying to fold things flat. And we like flat foldability because we like it for packaging purposes.
But if they're in the same stream, why does it fold? I mean, why does it fold off?
So there are many set sort of geometric arguments. You can just, so flat foldability means set all of these angles to pi or minus pi and see what the solutions are. And you'll find, I mean, that's the way I do it. You'll find that opposite sector angle sum to pi, because the sector angles are embedded. This one is associated with this tangent. So the sector angles are sitting in the rotations in this notation. And so you set all the angles equals to pi, and you'll end up with this opposite sector angle. I don't have great intuition for why that is, but it's a.
Because the rotation is, I think I can.
If you think of it, it's like a 4-bar linkage. You got 4 lengths, and so your lengths are directly related to those angles. So to get a 4-bar linkage to come flat, you need 2 lengths to match the length of the other 2 lengths. So that's where you get your angles. It's been proven in I think 3 or 4 ways.
Yeah, there's many like, this is a very old statement about origami. This is one of the sort of classical statements. It's central, but it's a necessary condition. So we stick with the necessary conditions. And the point is, okay, so we have that necessary condition that Krishna was talking about. And then, you can classify these rotation angles, and you do. And the big point is, if you hand me one angle and you told me the mountain valley assignment, then in fact everything else is determined. You can't. The constraints are so rigid that that's the answer. So if you know one angle and the mountain valley assignment, you know everything. Okay, and the results are explicit. You can write them in this way, but the actual formulas are not that big of a deal. Okay, so at this point, we've solved a single vertex, so you got a long way to go if I'm going to tell you all possible patterns. And so I just do the next simplest thing. Well, the next simplest thing is to think about 2 vertices together, but that's actually easy. So that's actually not hard to do compared. So let's do the next simplest thing, which is to talk about what it means for a panel and the vertices surrounding Q to be flat, rigidly and flat foldable origami. And so the way this is going to work is, I'm going to remember that if you hand me the mountain valley assignments, okay, and you hand me one angle, then everything else is determined at a vertex. So if you hand me this angle, this I call omega A, and this mountain valley assignment, everything is determined. So that means that this angle is determined. But since this angle is determined, everything is determined. So that means that this angle is determined. But since that's determined, everything is determined. So then I go down here and everything is determined. And then everything is determined. But now I have a potential inconsistency. And I don't have an inconsistency as long as these maps compose together in such a way that when I go around this loop, I end up back where I started. So that's the compatibility condition for folding this pattern as origami with folding angle omega A at this crease. That's the compatibility condition for this. And we want it to be rigidly and flat foldable. So what has to happen is actually you know, you have these folding angle functions that I wrote down previously. They're complicated. But actually, when you compose them together, because this should work, you know, as you fold it continuously from flat to folded flat, you should actually have that this composition of maps is the identity map. And that's the compatibility condition for rigidly and flat foldable origami for this particular pattern. And this is really the crux of the problem. So in order to solve the problem, you have to solve this problem. You have to say, given a set of 4 mountain valley assignments, which are denoted by, in this notation here, and a bunch of sector angles. So you can convince yourself that for a pattern like this, it's parameterized by 4 mountain valley assignments and 1, 2, 3, 4, 5, 6, 7 sector angles. You have to identify all possible parameters which solve this composition of maps equals identity. And that's only to solve for the 3x3 case. And you know, in fact, this is an example of those maps. So you compose them together, you put them in Mathematica, you go, oh, oops, that's not a good idea. So you have to do something clever. Okay, so what happens? It turns out that all of these maps share a structure. They all belong to what's called an abelian group. And what that is basically you can write them as a function of the angle gamma, but also of a parameter, which contains all the information about the sort of the sector angles at all the different pieces. And okay, why is that important? Well, what I can do is actually think a little bit about group theory. And the second sort of miracle is not only do these functions belong to a group, but if I take 2 functions and I compose them together, which is what we're doing here, then it turns out the product is actually this parameter mu1 and mu2, you just multiply it together. And so it basically, the composition forms another element of the group, and you can either compose them together or you can multiply these 2 numbers together and they're equivalent. Okay, and so why is that important? Because composition of maps is hard. Multiplication of numbers is less hard. So you get to replace a problem of composition of maps equals the identity with the problem of multiplying numbers together and setting it equal to 1. And so you can try to solve this problem, and that's the problem that we ended up solving. And so it turns out you can completely characterize that problem. And what you end up finding, forget what this says, but just think about this. What it says is that if you hand me the mountain valley assignment and the sector angles at 3 of the 4 vertices, then either there's no solution, which, okay, that's boring, or there's a unique one. The 4th vertex is uniquely determined. So if I told you how to fold 3 of the 4 vertices, then the 4th one is uniquely determined. And that actually solves the problem completely. And how does that solve the problem completely? Well, imagine I decided to tell you how to fold this line and that line. Okay, and I'm just drawing the squares that represent the topology. Well, then I just apply the theorem over and over again. I know 3 of the 4 vertices, so the 4th is determined. I do it again and again and again and again and again and again and again until I discover my crease pattern. So I discover the whole crease pattern by applying conditions on the left and the bottom boundary. So that's our recipe for understanding this problem. And so sort of just to reiterate, I apply the angles on the boundary here and the angles on the boundary here, and I apply the mountain valley assignments there, and the whole pattern is determined inside. And okay, there's also some issues with the length. If you know the angles and you know the lengths on the boundary, it turns out that the lengths are also determined. So everything is determined from the boundaries. So I basically take information on the boundaries and propagate it to determine the crease pattern. And since we did this kind of in a continuum mechanics way, we know the kinematics too, because we were building these things by using composition of rotation. So we know the kinematics. So what I can do is I can write a deformed configuration where I identify all the vertices as yij's, and there are parameters sitting on the boundaries and a fold angle omega. And this describes my origami. And so when omega is say pi over 4, it's this picture, and then as you evolve it, it goes from flat to all the way folded flat. And so that's great. So let's try to do something interesting. So can we solve an interesting kind of engineering problem with this description? And so the goal that one problem that we were interested in solving was, can we develop deployable origami that approximates fairly generic surfaces? So how do you think about this problem? Well, you have this explicit marching algorithm, so I'll call it a marching algorithm. And it's very nice. The computation is linear in the number of panels. So it's about as fast as it gets to solve these kind of problems. So we basically used that fact and did a lot of sort of engineering tricks to try and optimize the surface. So the idea is you have some desired shape. And essentially what you do is you discretize the shape. You use some standard ways of thinking about discrete surfaces. And so you put that into a big vector, and then you discretize an origami surface, and you put that into a big vector. You discretize it in a way that you're only going to consider things on the top part of the surface. And now you have all these parameters, and you can think about an optimization problem where you're trying to seek an optimal set of parameters that achieves the targeted surface. And I typically, you have to choose an initial condition for these optimizations. And so I study slight perturbations of a mirror aura. This is heuristics that's well known from the group of Mahadevan, is that perturbations of a mirror aura work really well to approximate lots of surfaces. And so, and you have to have good discrete approximations. And we did a lot of this, and there's a lot of numerical details. But if you're interested, we have a paper on this. And in any case, we perform these optimizations, and you can just see if it works. And it works quite well for many examples. So here's an example. This is the theory. That's the experiment. It's deployable, so it has this one parameter family of motions that's easy to fold, and it achieves this satellite shape. Here's say a vase example. Again, this is the theory. This is the theory too. So we have a design, and then we achieve this surface that we're trying to achieve. It folds all the way flat, and it has this easy motion. And we did some experiments, and the experiments look really good in comparison to the theory. So this is just to show that we did a lot of perturbing of mirror auras. If you know a little bit about origami, our algorithm is general enough that you can try to change the mountain valley assignments in places, and you can get interesting behavior like this kind of phase transition. So this looks, everything is sort of oscillating, but then there's like a sharp interface here, which is kind of cool, intersecting two cylinders. So that's another example. And that's the origami stuff. So the key points here are, it's easy to approximate surfaces with a variety of curvatures. In fact, that's kind of interesting that, you basically perturb around things that look like this. You perturb the little sector anglers around these things, and you can get surfaces with positive Gauss curvature, surfaces with negative Gauss curvature. So Gauss curvature is like, it curves this way and this way, that's positive Gauss curvature. If it curves in the opposite sense, in the opposite directions, that's negative Gauss curvature. You can get things where the curvature is changing. And all of that seems to be accessible by perturbing one of these kind of mirror origamis. And that's typically not something that's easy to do in general. Here's another example, but there's still a lot of questions. So this sort of non-convex optimization, this is my colleagues at Peking University. This was their idea. When Fan and I developed the forward algorithm, they were like, let's just do this optimization problem. I'm like, why should that work? They're like, well, we can try. And it works really well. But why does it work? It's something that we're very curious about. And why are these perturbed mirror aura surfaces good candidates for all types of curvatures? Again, something that we're really curious about. And what we're really doing here is we're trying to take something that's oscillating a lot, and we're trying to approximate a smooth surface. I want to understand, is there some way to actually average the mechanics in the right way, instead of sort of doing this discrete kind of inverse design problem, figuring out what are the characteristic features of a homogenized origami structure, because it looks like they can achieve a lot of surfaces at a variety of curvatures. And okay, I basically would be trying to motivate the mechanics a little bit, and it turns out the origami problem is hard. So I'm going to motivate the mechanics by the origami problem, but I'm going to shift gears and talk about something that's planar in 2D because it's easier. And so now we go to kirigami. So here's a question. I want to think about these kind of complicated mechanical metamaterials under load. So we have this kirigami pattern. This is called the rotating squares pattern. What I'm going to do is I'm going to fix two of the corners, and then I'm just going to apply a load here. And I want to see what's going to happen to the pattern. And so what you get experimentally is something like this. Okay, you know, the slits open up. We're at the loading point, and you load it more, and you get something that's, I mean, so it's actually really kind of nice in a way. It looks fairly structured, but it's not uniform at all, right? So, you know, the slits are more closed here, they're open here, and the question is, can we model this in a way that we would actually be able to predict this behavior? And so, you know, I come at this from the origami view where I idealize everything as rigid panel motion connected along flexible hinges or flexible creases, and you go, well, go into your favorite editor and start drawing boxes and rotating them, and you see, well here it looks like I'm sort of just rotating these things, and if I go here, well, it looks also like I'm sort of just rotating these things. You know, maybe the overall deformation is consistent with a mechanism, and by mechanism I mean that it's consistent with if I idealize the panels as rigidly rotating across perfectly flexible hinges, maybe I can get this pattern. And so maybe that answers the question. It's just this rigid origami kinematics. So you can ask that question. Now it's the same pattern. This is just the open configuration of the pattern. And so I'm going to try to understand the rigid kinematics of this. It turns out to be a lot easier than origami. So how do you kind of understand this? Well, just take two of them and rotate them, call one rotation R and one rotation Q. And you can just try to ask, well, how do you make this thing fit together in a way such that all the panels are rotated and connected with each other? And so locally, that question is this. Well, I got to take this red bead and fit it back onto this guy in a way that I don't deform, that I only rotate these panels. And you can just do a little bit of trigonometry. And the answer to that question is that there's only one way to do this. You rotate this pattern, this one by Q, just like this one, and you rotate this one by R, just like that one. There's only one way. Okay, but that's actually enough to tell you everything, because you can play the same argument again. There's only one way to do this, and there's only one way to do this. And so what you find is that if I rotate two of these guys, then actually everything is determined. And more than that, this and this are all the same. So the deformation is periodic. So you try to do mechanism kinematics and you end up with this periodic structure. Of course, what you see in an experiment is not periodic. So you start pulling on the thing and it looks locally like this kind of kinematics, but if you look here, it's different than if you look over here. So this kind of kinematics does not explain the experiments. It's far too homogeneous to explain the experiments. And okay, so can we try to understand this? So I don't just want to try to understand the rotating squares pattern. I want to try to understand large families of patterns. And so you kind of look at this thing and you go, that's interesting. We have this RQ structure. Why is it that the mechanism kinematics are this way? Well, it's not because I'm dealing with the rotating squares pattern. It's more generally because the slits are all parallelograms. So it turns out if you have patterns in which the slits are all parallelograms, then it is necessary and sufficient that the mechanism kinematics has this kind of feature where you're doing these RQ rotations. So you can cook up many patterns in which the slits are all parallelograms. And if you think about unit cells, so patterns which are unit cells in which the slits are all parallelograms, it turns out that you can easily prove that if you start with a seed and you want it to be periodic, so like in 2x2 periodic, then it turns out that you just have to rotate the seed 180 degrees and that will generate a pattern, and this is necessary and sufficient for these types of patterns. So we can cook up many patterns in which the mechanism kinematics oscillate in this way. And here's a very generic example of these patterns. And my experimental collaborator, Paolo, can do experiments on various different types of patterns. So this is the rotating spurs. This is another pattern which falls into this family. Again, what you observe is inhomogeneous deformation, but mechanistically, these are all sort of this type of homogeneous kind of actuation. And so the experiments are all inhomogeneous, but the mechanistic response is homogeneous and periodic. So it's not explaining how to explain the experiments. Okay, so how do you actually think about this problem? So let me take one of my generic patterns here. And let's observe some things. Okay, I have this pattern. I can draw some vectors on it. So S1 through S4 produces a vector S. T1 through T4 produces a vector T. And what you can observe is that if I just take my unit cell, which is these two, and translate it along S or translate it along T, I generate my pattern. And okay, in fact, if you deform this unit cell as a mechanism and then take the deformed unit cell and translate it along its deformed S vector and T vector, it generates the deformations of the pattern. So this S vector and T vector form a Bravais lattice, if you know kind of crystallography. And what we can do, because we know the mechanism deformations, we can easily sort of calculate how S is deforming to S def under a mechanism deformation, and how T is deforming to T def under such a mechanism deformation. Remember, we have these RQ things. I'm going to change my notation to write this as R gamma plus XC and R gamma minus XC. It's perfectly equivalent, and draw little pluses and minuses because it makes the picture look cool. But you know, you can do that and think a little bit about how S deforms to S def. And if you just sort of calculate how, you know, S1 deforms with the plus rotation, S2 deforms with the plus rotation, S3 the minus, and S4 the minus, and you do a little bit of algebra, and you get these types of equations. And you know, our ideas kind of using the Cauchy-Born rule, if you're familiar with crystallographic theory, what we just do is, you know, we simply relate S def to S through an effective deformation gradient and T def to T through an effective deformation gradient. There's a unique effective deformation gradient that takes the ST lattice to the S def T def lattice. And you know, by this formula, you can see that it's some kind of thing that depends on gamma and XC. It depends very simply on gamma and depends more complicated on XC. So F effective is R gamma, so this is a rotation by gamma in the plane, times some tensor A of XC, and A of XC is complicated, but that captures all the dependence. And so the key idea in this type of analysis is, okay, this is just homogenizing the pure mechanism deformation, but now I have a continuum deformation gradient. And so what I can say is, well, you know, there are many unit cells in the pattern, and if I just zoomed in at a single unit cell, it looks a lot like a mechanism deformation of the pattern, but just zoomed in at the single unit cell. You know, it's just different in different places. So since I have a continuum deformation gradient, just allow it to vary spatially. So replace my homogeneous effective deformation gradient with some deformation gradient that is varying spatially, so grad y effective, which is varying spatially in X. And then, of course, the right-hand side has to vary spatially, and the only things that it can vary in are gamma and XC. Those are the kinematic variables, so you just let them vary spatially. And maybe that's the theory that makes sense for predicting these types of shapes. Okay, you know, you try to write this down, and of course, this is going to induce a lot of compatibility conditions. The left side of this thing is a gradient, and it's not obvious that the right side is a gradient, so you can take its curl, set it equal to 0, and you derive another condition. You can take this curl and set it equal to 0, and you derive a governing PDE. So you have basically a PDE, it's called a quasi-linear PDE, and what I'm claiming is that the solutions to this quasi-linear PDE are actually governing the soft modes of deformation that you see in this type of system. And so let me just clarify what this PDE is. So XC is related to how the slits change as they open and close. So XC is an angle measuring the change in the slits as they open and close. And gamma is a rotation angle you can think about gamma as being a rotation angle of each individual unit cell. It's of course being sampled in space in a in sort of a discrete way, but it's a continuous angle field, and C is also a continuous angle field that are being sampled in space in a discrete way. And that's this PDE that you want to solve. And you want to compare it with experiments to sort of get some sense of whether you're on the right track here. Anytime you have something that's not a nice linear PDE, the first thing you should do is you should linearize it and study the linear PDE. So let's pretend we have a solution to the nonlinear PDE. I guess my laser pointer is gone. So pretend we have a solution, perturb it and see what the perturbed PDE does. So you end up with a linear PDE that you have to solve. It's a second order linear PDE. These have classical characterizations. And it turns out something very interesting emerges. So the linear PDE happens to be what's called an elliptic PDE, if and only if the pattern is auxetic. So an auxetic pattern is something when you pull on it in this direction, it wants to expand in the transverse direction. It happens to be a hyperbolic PDE, if and only if the pattern is not auxetic. So you pull on it this direction, you get what a more conventional Poisson's ratio where it contracts. And this is a very powerful statement because elliptic and hyperbolic PDEs have very different properties. So an elliptic PDE, if you sort of think about the variables in which you're solving the PDE, the maximum and minimum of the variables actually occurs on the boundary, never on the interior. Hyperbolic PDEs describe wave-like phenomena. So the way you should think about the distinction between these things is elliptic decays. When you apply something on the boundary, it will decay into the interior. For a hyperbolic PDE, it will actually propagate far into the interior because it's like a wave-like phenomenon. So you apply a perturbation, the perturbation goes through the whole sample. So that's the way you should think about these things. And also, I should point out that the characterization, must have been a different slide than the one I used previously, but the characterization also holds in the nonlinear setting. So you do the linearization, you classify the PDE, and then you recognize that by PDE theory, it holds also in the nonlinear setting. So these types of properties are also good in the nonlinear setting. Okay, so we have our characterization of the PDE. We have experiments, and you can sort of plot the slit actuation field. That's that exceeds. So how much the slits are opening, and you can color that in a nice way. And this is what you see for the experiment here, and this is what you see for this experiment here. This one, according to our characterization, is not auxetic and thus is associated to this hyperbolic PDE. This one is auxetic and it's actually conformal and associated to the elliptic PDE. And you can kind of already see it. You know, these things are spreading out. This is being loaded like this. And so this is spreading out kind of in a conical way. And these things are sort of decaying along ellipses. Yeah.
So there are the characteristics in the hyperbolic PDE case, the boundaries between similar definition. What are the characteristics? It looks like there's a sharper transition, right?
Yeah. So actually, so can we solve the PDEs? We actually solve for the top one. We use the method of characteristics, and so this relates to trying to find eigenvalues and eigenvectors of this gamma tensor here. And so the eigenvectors of that tensor, I believe, or their orthogonal, I forget. It's either the vectors or their orthogonal complement are the lines in which the constant actuation. So you sort of see these kind of lines of constant actuation that go all the way through the sample. Maybe not so great in the interior, but kind of along the edges here. And so we solved the PDE using the method of characteristics. We found what are called simple wave solutions to this PDE. This one turns out to be what's called conformal kirigami. And conformal maps are well studied using complex analysis. So we know tons and tons of conformal maps. So we basically tried to map this to a conformal map. And so this is our best effort to find solutions to the PDE that kind of mimic the experiment. And this is what we get. So here you can see clearly that you have characteristics kind of going out like this. And you have this red region on the interior. And then this is our best conformal map solution of this system. And you may say, okay, well, that, the fit is not perfect. But yeah, go ahead, Krishna.
Can you make lift, can you lose strong lift?
Yes.
Okay.
Not in this example.
Okay.
Can, depending, because there's a huge design space. This is just two designs in our enormous design space. You can change the PE type under that. And we've been trying to find a good, convincing experimental way of seeing this. We haven't discovered it yet. But yes, so we've been trying to play that game. But I want to bring out that this is, you say this is not really maybe a perfect fit, but in fact, there's nothing to fit. These are all parameters of the unit cell in here, and I'm solving a nonlinear PDE and I'm preparing it to an experiment. So there's absolutely no fitting parameters other than you're just trying to find the best solution to a nonlinear PDE that you can find to match this. So that's a pretty strong result. And so I have about 10 minutes. Okay, so I want to, the way I explain this thing is kind of, we have a homogeneous effect of deformation gradient. And then, but that's not what we observe in the experiment. And so let's just replace this with something that is varying spatially. And that's a nice explanation, but it's sort of a lie. It's the explanation that serves the purpose to the sort of the paper that we were trying to write at the time. So this locally mechanistic leap of faith, I call it, actually has some meat under the hood. So how do you understand this type of analysis here? And so one thing you can do is you can try to sort of construct a deformation. You can assume a solution to the PE and then try to sample it and use that sampling to construct a deformation which will match in some approximate sense what you actually observe experimentally. And so that's something we tried to do. So think about a pattern, a fairly generic pattern. It has a characteristic length scale L, which is the cell size over the sample size. And here I'm zooming in on this pattern, and you can construct an ansatz, assuming a solution to the PDE. Looks something like this. It has the parameters gamma and xc and y effective sitting inside of it. These things are solving my PDE. And you can just see what it actually means. So because I don't have a mechanism deformation, this is a bunch of rigid motions of the panels, but I don't have a mechanism deformation. Actually, you're ungluing the pattern when you do this construction. So you unglue it, and you have gaps that form because you're basically pretending that they're not connected, and you're just rotating them according to some sampling. And okay, but you can calculate the gaps, and you can try to see what that actually means. And so intuitively, this is a construction, okay, this is a mathematical construction, but these gaps encode some sort of elastic energy because you have to close them in the real system. So what does it mean to be small gaps? So that's the question. And so you can calculate the gaps, you prescribe one of the translations in a natural way, and it ends up with this characterization. The gaps consistent with the cell size over the sample size are have a formula R times A minus grad Y effective, and then plus higher order terms. But this is in fact our PDE. So our PDE actually says that if you solve the PDE, the gaps are small compared to the cell size over the panel size, which means that it's sort of vanishingly small elastic energy in some sense. So PDE is sufficient for small gaps. And I've been working with a mathematician for a while to try and prove that the PDE is actually necessary for small gaps. And so I'll just kind of throw this up here and try to explain what it means. So, imagine you have any deformation, just any deformation you want of these types of systems, and you're interested in deciding whether you can estimate the elastic energy in some reasonable way. So to a mathematician, a reasonable way to estimate the elastic energy is to say, I'm deforming this thing, compare it with an ideal mechanism, take its difference and square it. And the question is that a reasonable measure of the elastic energy? And what my colleague Ian was able to show is, in fact, yes, you can bound this thing from above by the elastic energy, except you have this funny little log term. And it turns out that log term is very physical. So this L is like the characteristic length scale of my panels or my cell. This delta is the characteristic length scale of my hinges, which are actually not points, they're real hinges. And what this basically says is, oh, as long as delta is big enough, then you can replace your elastic energy with some sort of discrete elastic energy. And that will do a good. But once your delta gets really small, then you can create really diabolical deformations of the cell at very little elastic energy. So this kind of inequality doesn't become so good. After you kind of do this inequality and you do a lot more analysis, it turns out you can prove that the PDE that we wrote down is actually necessary for sufficiently small elastic energy of the system. And so that's still work in progress, but the PDE is a good idea for measuring the soft modes of these types of systems. And just a final remark, so the fit wasn't perfect for solving the PDE, but you can cook up, once you know the PDE, you can cook up kind of a constitutive model that's easy to implement in like Abacus. And we've done that. And you have to fit some parameters, C1, C2, C1, C2, C0. And if you fit them reasonably well enough, then you can get an FEM, like a continuum FEM, that does a very good job of matching with lots and lots of experiments. So we're developing broadly applicable constitutive models along these lines for this system. And with that, I'm happy to take any questions.
Lots of questions, but I'll give it to the audience. Vikram.
Hey, Paul, very interesting talk. So now that you have an strain energy density with the local deformation metrics that you have you've come up with, could one ask a further, let's say, design on an inverse problem, which is how do you, for instance, maximize dissipation?
Yeah, so this is like a really, this is sort of a really important question, which is intuitively, so, we have this PDE we cook up, and then sometimes it's elliptic and sometimes it's hyperbolic. If you wanted to sort of protect something, you want energy dissipation, the intuition is you should design something that's elliptic, or design something that's auxetic, because that should dissipate a lot of energy, because you hit it on the boundary, but the actuation decays on the interior. So if something is far away from the boundary, it doesn't actually feel it. And then if you want to have easy communication using mechanical actuation, you should design a system that's hyperbolic, because you perturb the boundary and that information propagates far into the interior. So we're thinking a little bit along those lines, but it is we haven't really gotten far in trying to understand how to do dissipation and quantify dissipation and really do dynamics, because at the end, that would be kind of like interesting for like damping and dynamics problems. And but how do you tune the sort of the dampening coefficients in these systems? And I haven't thought about it too much.
Same design space that you initially worked with.
So our current strategy is very sort of start out as general as you can and see what happens. And so this design space has this kind of some are elliptic and some are hyperbolic. And so I guess my answer to that would be, I want to try to understand very general design spaces and then start exploring within them. So start general and then see if you can answer those more specific questions within that design space. But if you want, I don't know if these are the model system for this type of question, but I think we can begin to ask these questions in a more systematic way once we have these types of tools.
Yeah, I think so. And just as a continuation of that, like you could probably look at generalized stresses possibly.
Yeah.
And then see which designs, like for instance, if you have a sheet with a circular hole,
Uh-huh.
I mean, which design like machines the stress much more.
Yeah. So, so what Vikram is I think what Vikram is also saying is, most of this is just kinematics. There's no elasticity built only at the very end did I put in some elasticity, which is this kind of a model. The kinematics are sitting here. And then, you choose whatever, I choose for this one. I choose a compressible Neo-Hookehead type model. And now I'm starting to build in elasticity. Actually, kind of, Vikram, what we've been doing is trying to actually calculate the elastic energy. So the real deal elastic energy. So that's kind of been a fun topic that we've been working on recently. And so we might actually have the generalized stresses soon for the actual elastic problem.
Yeah, it's really cool so far. I'm curious about so you have your elliptic system and your hyperbolic system, which you sort of picture here, right?
Yeah.
So, I mean, it looks to me, and this is naive because, I'm not versed in the subject completely, but, it looks sort of like, your angle, I'm not sure if your C is measuring the amount of opening it can go up to. So you have like a limit on C in the latter case, right? And in the former case, like you have a total opening. Right, which can provide for more insight.
Yeah.
What happens in the middle, like that crossover region? There's a certain point at which you hit, like your mesh is open enough, right?
Yeah. So
Like,
once
what happens to the
once it's open up, okay. So your intuition is right. What happens when it opens too much, or when it gets fully open? Then this PE breaks down, and you actually start stretching it. You're actually really stressing the system. So if you pull too hard.
No, sorry. I mean like in the initial setup, say you're in the reference configuration, right? But like the initial reference configuration of your unit cell, right? If the angle, like you have your squares, which is like a 0 angle this chart, you have your linear case, your diamonds, it's like let's say 45-degree angle.
Sure.
If you're at like 20 degrees,
Oh yeah,
do you
there's
cross over from like what's
no. So this dichotomy between elliptic and hyperbolic is not so transparent in the way you want it to be. In fact, hopefully I can get this back. Let me just try sharing my screen again.
That's also interesting.
So it's not so transparent. In fact, it was really hard. So when we wrote our initial paper on this subject, we did it for these what are called rhombi slip patterns. We did this this relationship between ellipticity and the Poisson's ratio for what are called rhombi slip patterns. And then they wanted us to generalize it to the more general family that we cooked up, which looks like this. And I can't. This is either elliptic or hyperbolic, and I can't tell without calculating out this A tensor and doing some work on it. So it's very not intuitive to me when it is elliptic and when it is hyperbolic. Yeah. Yeah.
Well, brief talk. Two questions, somewhat related. The first one is on the sheet match. So you say you start off with the mirror perturbation.
Yes.
What other? Well, I guess one is how susceptible is your final design to the perturbation?
Absolutely, extremely susceptible to the. These are non-convex optimization problems sitting in a. You basically, I mean, what I thought was surprising is that you can start with a mirror aura as your initial condition, and you can get all sorts of designs that match all sorts of curvatures. And so this mirror aura happens to be a really good starting point for these non-convex optimization problems. And I give credit to like Mahadevan and his group for that, because I wouldn't have thought that that was a good idea. And they did it for a different class of problems. And but to your point, I think your question is like, how do you choose the initial condition, right? And I don't know the answer to that question. And it's something that I really, that's why I kind of want to replace these non-convex problems. I'm doing some work with a student on machine learning, and I'm hoping to try to learn sort of how to do this inverse problem without by skipping that step in some reasonable way. Because to your point, we can't just be relying on what we always in some sense, I'm still relying on what people have already known, right?
That's my next question. All of these are quads. What about non-quad type acts?
Yeah, so I'll answer that question the way Robert Lang would answer that question. And, origami kinematics is like counting rabbits, and you're like 1 rabbit, 2 rabbits, 10 rabbits, 150 rabbits. It turns out when you go away from quad meshes and you try to start doing these, so what there was nothing really tricky about what I did. I'm just solving a series of local problems and then piecing them together. But when you go to like higher order meshes, where you have 6 folds on the vertex or something more complicated than that, the counting problem gets really hard. So it's hard to think of using these local characterizations as a systematic strategy to understand the deformation modes. So I don't actually have a good answer to that question for sure. Yeah.
So starting with origami, you had a rigid plate, and going on to kirigami, I presume everything is maintained in plane.
Yes.
If you think about deviating rather in shapes, deviating from those hard rules, is there also another path to follow with small deformations?
With small deformations. So
Non-planar in origami, or non-planar in the kirigami,
Yeah,
and non-rigid in the origami.
So non-rigid in the origami is really our next step. So this kirigami problem is really the toy problem for trying to understand why this is a saddle. Because this is our first introduction into. All right, so
Is that non-rigid?
this is
What you just did by hand?
yeah, this
You
is
say that
definitely
has to be non-rigid?
definitely non-rigid. This requires bending of the panels, and so you need to sort of figure out how to bend the panels. In this case, the deformations that we're describing here are soft but non-rigid, and one of the ways we figure out how to understand these things and is by this little gaps thing, which is also kind of a goofy calculation. I break up the pattern and I calculate the gaps, but it makes a lot of sense actually that this is proportional to the stored elastic energy of the system if you think about it a little bit. And so that you can kind of do the same idea with the origami kinematics. You can break up the pattern. You can add what are called bending creases in this system, so add some flexibility, and then try to calculate gaps, and you can do the same thing, derive kind of the same coarse grain models. They're more difficult to derive and kind of understand, but that was really the next step there, going non-rigid in the origami. And then going out of plane in the kirigami is also interesting. There's a lot of flexibility when you go out of plane. These things have a single degree of freedom motion in plane. If they buckle out of plane, you can construct all sorts of mechanisms that map this planar thing to some three-dimensional structure. So most of our experiments involve pulling, because you're not going to buckle out of plane when you pull something. But if you try to compress it, it can do a lot of things. So that's a harder problem, I think, but something worth thinking about for sure. Yeah.
Okay, for the sake of time, I think we'll just thank our speaker, and please come again, Paul. That was great.
Thank you.